Students, in our first lecture of this series, we discussed CR equations, Cauchy-Riemann equations. These equations are conditions, necessary conditions for a complex function to be differentiable at a point. Now, they are only necessary conditions, and let me show them. Suppose we have this fz as our complex function with z as complex number. We can, as you have seen in that lecture, we can always write it in the form of, say, this we can write fz is equal to u plus uxy plus I vxy. I will not repeat it because I have already shown you how this u, real part of this complex function, and imaginary part of this complex function, how they are functions of x and y. I had used an example here in that lecture, and we will assume that you know that you have gone through it. Now, CR conditions state us that partial derivative of ux, with respect to x, partial derivative of u with respect to x, that is, which is of course denoted by ux, is equal to partial derivative of this v with respect to y. One condition. Another condition is partial derivative of u with respect to y is equal to negative of partial derivative of v with respect to x. These are these CR conditions. Remember that ux means that means del u by del x. Vx similarly means del v by del x. Del v by del x. And you can think of other derivatives like that. Now, our this present lecture is about what are the sufficient conditions for this complex function to be differentiable at a point. It turns out that they are sufficient conditions or just CR conditions, these Cauchy-Riemann conditions, but with one additional thing, that is the partial derivatives, that is ux, uy, vx, vy, they must be continuous. Partial derivatives not only need to exist, they must be continuous partial derivatives, continuous PDs, partials, or simply we can say continuous. These four should be continuous: ux, uy, vx, vy. They should be continuous in some neighborhood of that point, of course. Now, why? The question is why. Normally, when you think of this continuity, suppose you have a single function, a function of single variable, and you say that this function is continuous at a point, say x equal to a, if it satisfies three conditions. If it satisfies this condition that fa exists, fa is there, it is finite, fa is it exists. Number one. Number two, limit x tends to a from right should be equal to limit x tends to a from left. There are in case of single variable function, there are only these two possibilities. X can approach a only along two paths, because the function is a single variable function and is hence confined to a single dimension. So if suppose this is x here, a here, and then x can approach a from this side, x can approach a from this side. These are the only two possibilities, and these two limits must come out to be equal. And third is that limit x tends to a, fx must be equal to fa, that is, limit must be equal to the value. These are the three conditions that a function of single variable has to satisfy at a point so as to be continuous there. But if you have a function of two variables, then something more is required. Suppose you have fxy now, a function of two variables. this condition is as it is for a single. That means first condition is that FAB. Now the point here is not A, point here is AB, because it has two these coordinates. Now FAB should exist. Okay, number one. Number third, that is limit should be equal to limit x tends to xy tends to, sorry, now you have xy tends to AB fxy must be equal to, now it must be equal to FAB. But the middle condition, this middle condition here is a more complicated thing. Why? Because in case of a function of two variables, there are not just two ways in which the transition coordinates, in which the transition coordinate means changing coordinates, this x can approach a fixed point. There are infinite such ways. How? Because in case of a function of two variables, you have the domain of the function is not a single line, it is rather a plane. You have x here, x along this, y along this, and the function can be represented along this z-axis. Now you have here these points form the domain of the function. That means inputs of the function can take values from these points. Of course, with certain there may be restrictions, but whatever point, there will be at least some region in which the function is definable. Suppose this is the region in which the function is definable. Now, this is the domain of the function. Domain of the function is not now a straight line. It is not a straight line. It is a plane, a piece of a plane. Now this means that you have, now you can, suppose you want to check the continuity of the function at this point, say AB is the point where you want to check the continuity of the function. Then you can approach this AB from infinite directions. You can approach along this direction, you can approach along this direction, you can approach along this, 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 and so many directions. Now it is humanly not possible to check each and every direction, because there are infinite such directions, and thereby to ascertain whether limit exists or not. See, limit will exist if the value of the limit does not depend upon the direction of approach. That means if the value of the limit turns out to be same along all the directions, then only the limit exists. And if limit exists, then alone we can say that the function is continuous. So there are harder conditions. That means there are more strict restrictions on continuity of a function of two variables than on continuity of a function of single variable. Now question is, how can we then ascertain whether a function is continuous or not? I mean, fxy function is continuous or not. Practically this method of approaching from infinite direction is not possible. So people have now devised it. They have created methods, indirect methods, by which one can ascertain whether this function is continuous or not from different directions. But that's not our topic. That's a big topic in itself. How to test continuity of a function of two. It is this multivariable. We call it multivariable calculus. So we do not have that. That is not in our syllabus, and we will avoid that at this time. But the essence of this, we will definitely go for that. What that is, see, you have seen that. We have to now why continuity is being discussed here in this topic, because continuity is the requirement for differentiation. If you want to check whether a function is differentiable at a point, for example fxy is differentiable at AB or not, the first thing that it must satisfy is that the function must be continuous at AB. It must be continuous. Continuity is must for differentiation. The converse, of course, is not necessary. A function may be continuous yet not differentiable. So, but For a function to be differentiable, it must be continuous. So that is why it is important. Now the question is, in case of these complex functions, you have ux, u and v. Suppose u is continuous. If u is continuous, only then you can define ux. If v is continuous, then only then you can define uy. You can define ux, uy here, and similarly vy and vx here. So because derivatives can be defined only if the functions whose derivatives they are continuous. Okay, that's okay. That means ux, u and v have to be continuous for the existence of these partial derivatives. So partial derivatives must exist. Now, this partial, if u and v are continuous. The unique condition and the strange condition here for this differentiability of complex function is that not only that partial derivatives must exist, they must also be continuous. That means not only u and v must be continuous, but ux, uy, vx, vy must be continuous. If that is there, then the function is then differentiable at this point or in the neighborhood of this point. If not, it is not. Why should these derivatives themselves be continuous? If the underlying functions are continuous, nothing strange about that then. But if these are being demanded to be continuous, that is a little bit strange. Let us see why. You'll ultimately see that this is all consequence of these multipaths. Now, why? Let us see. Let us go for that. For that matter, let us do one thing. Suppose we have a point here in plane. Let us denote it by simplicity. Let us denote it by P naught. And let us approach this point by an arbitrary path, say like something like this. You are approaching this point P naught along this arbitrary path. Say arbitrary path, call it C, for example. Now you have consider a point P on this path. Consider a point P on this path. Okay, this point P and this point. Let me take this point as the point where I have to approach, and that is what I am actually doing. I am approaching this along an arbitrary path, not parallel to x-axis, parallel to y-axis, which we did in deriving CR conditions, CR equations. But here it is different. It is a different story. We are taking an arbitrary path. Now that is good. Now next, we can define this PO. Let us first make certain things clear. This PO, since we are dealing with complex function fz, let PO mean z naught, z0. That means z naught. I will not write here z naught, but you'll think about it that here value of z is z naught. Okay, here value of z is z. Nice, that's okay. Now let consider this path. Okay, let's define now. Let this be delta z. Now let's define now derivative of fz at 0. The derivative definition is, as usual, that is equal to difference quotient divided by of course difference quotient, that divided by delta z, of course with a limit. Sorry, I have to write this here better here. F dash zo, that means derivative of this function at zo is equal to limit z delta z tends to 0. I will take one value of function here, one value of function here. One value of function here is, that is f. I can take f p value of function at this point minus value of function at this point. divided by delta z. Now value of function at p point. You know that value of function fz is uxy plus I v y x y. That means there's a real part and an imaginary part. Using that fact, I can write limit delta z tends to 0. I can write up. This will be fz will be equal to fz at p will be equal to up plus I vp ivp. Good. Now then I will have this minus upo value of function at po plus ivpo. That is it, divided by delta z. Okay, now next we will do one thing. We will bring these two in on one side and these two on the other side. Then we will have we can do it here. Let us do it here. That means f dash z is equal to up minus upo plus I will be taking as common, and we have vp minus vpo divided by delta z. Okay. Now I will use mean value theorem for two variables. Now that but before using that, let me transfer this whole material to this. Let me write it here. F dash z. I have reached this stage where I have f dash z is equal to up minus upo, vp minus vpo. Rest you can easily remember. Up minus upo plus I vp minus vpo. Okay, divided by delta z. Limit delta z tends to 0. That is okay. Now we know that u and v are continuous. We assume that they are continuous. This will enable us to use this mean value theorem. Just let me write it first one. Now the mean value theorem. We know for a single variable, if you consider mean value theorem for a single variable, it simply tells us that the for a function, a continuous function, of course, function should be continuous. For a continuous function, the average rate of change of the function over a certain interval is equal to its actual rate of change at some point inside the interval. That means suppose a function is defined in this interval, AB interval. Let me not write it AB. Let me take it as RS interval. A function, because I have avoided AB because I am using AB somewhere else. RS. The function is I'm talking about a function of single variable fx, because that will enable me easily to switch over to function of two variables. Now fx, in fact I have discussed this. I think I have anyhow I will go for a quick review of this. A function fx is defined in this interval. It is something like this. Let it be something like this, or this be s here. The rate of change of the function changes. The function has a slope that changes. But if we take average slope of this function between these 2 points, that will be fs final minus initial value, difference of this initial value, divided by or s minus r. This is rate of change of the function over this interval. rate of change of the function. According to mean value theorem, there will be a point somewhere between R and S, somewhere. Say here, so call that point C. Let me call that point C. This point will be such that at this point, rate of change of the function, actual rate of change of the function, will be exactly equal to this average rate of change of the function. That we say that f dash C, this will be equal to f dash, that is derivative of the function at C, actual rate of change of the function at C. This is mean value theorem. It is something as I had given you as simple example. Suppose a car starts from rest and then travels a distance of 20 meter in say 5 seconds. So it is average. If we calculate its average speed, that average speed will be distance divided by 5. That will be 4 meter per second average speed. And when the car accelerates from zero speed to some speed, our theorem says that the car will definitely attain a speed of 4 meter per second somewhere in this interval, somewhere in this, provided that the speed of the car is not quantum mechanical, so that it will experience jumps. So it is a continuous thing, a continuous variable. We are sure that it will pass through this value as well. That is the essence of mean value theorem for a single variable. So if we can write, then if we have a mean value theorem like this, we can write it as fs. For example, say this was rs. S is final point, the end point. Now I can write it in terms of value of the function at the end point. Sorry. Now f, I can write it as this. Fs is equal to I can transfer all these. First let me cross multiply this with this. F dash C S minus R, that is interval, plus FR. Finally it will be there. Or simply the final value is equal to initial value. FR is the initial value. Final value is equal to initial value plus C plus what? Plus rate of change plus derivative. Actual rate of change plus derivative into interval. That means separation between final and initial. Okay. So this is the situation. We will use this theorem if we have, suppose for example, a single variable function. It is quite easy to use, but for a function that has two variables, you have to use two derivatives. First you will have to take derivative with respect to x, then you will have to take derivative with respect to y. When you take derivative with respect to x, you will have to multiply it by interval delta x. And when you take derivative with respect to y, you will have to multiply that by interval delta y. That is all about mean value theorem for two functions. That means for two functions, two variable functions, it is fs is equal to fr final, or that is, or we can write it like this. ff means final minus initial here, final f function value, initial value fi initial, plus derivative with respect to x ux into interval delta x, plus the value of yes is not only derivative. There is one more thing that we must consider, is that is very important. That is not only derivative that you will write here. You have to take that value of the derivative at a point. And this is true for a particular point between in this interval. So derivative at that specific point, the point will lie between R and S. Let that point be, say, let's call that point Q1 point. We will show you here in this particular case, into delta x plus uy q1 into delta y. Now this is the, here you are taking derivative with respect to x, here you are taking derivative with respect to y. Now, and evaluating that derivative at a particular point q1. It is not, mean value theorem is not true for every point. It is true for, that means speed of the curve will be 4 meter per second only at a particular point, not that it will be 4 meter per second everywhere. So with this, I hope, dear my dear students, you will now be able to use this theorem here. F dash z, we have till now we have this story. F dash z is equal to, you have this thing here, up minus u. F dash z is equal to up minus upo. Let's keep it like this, plus I vp minus vpo divided by delta z. I'm sorry, I have forgotten to write this limit. Okay, limit delta z tends to 0. Okay, now f dash z. Now, sorry, I will use mean value theorem now for this for u and v separately. Final value of u, first let me take mean value theorem for u. MVT for u. Okay. For u, I will take, say, for u, final value, as you know, let me write it here back. I have final value is equal to initial value plus this derivative plus this derivative. I have this final value. Why should I keep it? Yes, here. Let me write it here. Final value is equal to initial value plus rate of change ux evaluated at q1 into delta x plus uy evaluated at q1 into delta y. It is like this. Again, we go to our this problem, that is, here you have po, here you have p, and then you are approaching like this. You have, say, q1 is the point. Let q1 be the point at which the actual rate of change is equal to average rate of change. Mean value theorem. This is the mean value theorem point, q1, this. Now, applying MVT for u, then you have final for you are using it for u. That means final u, that is up final. I will take this final minus initial, final minus up is equal to fi, that is fi is upo, initial value of function, plus ux. Okay, q1 into interval, that is delta x, plus interval delta x into plus uy q1 delta y. This is mean value theorem. And then if I take this upo to this side, I will get up minus upo. I will get up minus upo equal to this thing, ux q1 delta x plus uy q1 delta y. So I substitute then up minus upo. I will substitute these. Similarly, vp minus vpo. When I apply mean value theorem to this v function, that will be vx evaluated at some other point q2. Let q2 be, for example, here. Why other point? I will tell you why. Vx into this delta x plus vy into q2 delta y. Why q2? Because v is a different function. U is one function, v is different. These are not same. They are different functions, and hence the mean value theorem point will not necessarily be same for them. That's the reason. Now, using these there in that this derivative, we have f dash z. F dash z is equal to you can yourself see now, it is equal to ux q1 limit z delta z tends to 0, ux q1 q1 ux q1, that is it, ux q1 into delta x plus uy q1 uy uy q1 into delta y into this is now we have the second part I okay, I need not this here. I is I into Vp minus Vpo Vx Vx q2 delta x plus Vy q2 delta y q2 delta y divided by delta z. Now I am going to break this ux q1 into two parts. Ux q1, value of the partial derivative at q1. See what I am going to write here. Instead of writing ux q1 here, I will write ux po here. This means that I will be actually then making an error. We will not, of course, we will keep track of that error. But first of all, let you do one thing. Let's explain it like this. I have ux q1. That means partial derivative evaluated at q1. Instead of this, I will write partial derivative x evaluated at p naught. How much is the error that I am committing? The difference of these two. That means ux q1 minus this. This much is the error. Suppose value of this is, say value of this is 16. But what I am doing, I am, instead of this 16, I am substituting a value that is 12. How much error am I actually committing? Error I am making. That is 16 minus 12. That is 4. Is that clear? I think it must be clear. So I will do one thing. I will write there. I will write here in its place. I will write uxpo. But keep the error separate. I will collect these errors separately, and finally add them back to this. This means that I will not let any error be actually made. It is only for time being. Now I will go to this. Before I handle this, I go to this f dash z. Let me tell one more thing that is very important. There are simpler methods of establishing this, but those methods are what they do. They actually hide the basic concept of this sufficient conditions, basic concept of analyticity of these complex functions. Those methods do not actually reveal why partial derivatives should be continuous. They simply, what people do, people usually simply skip and say it is needed for this, but actually not showing. It is better to understand the philosophy behind some method than to use shortcuts. Now f dash z, let us go back to this. We have f dash z is equal to, sorry I have forgotten it, limit delta z tends to 0. That's okay. Then ux q1 in its place, first let me write it here. F dash z is equal to limit delta z tends to 0. Then I have ux not q1 p naught delta x, okay, plus uy p naught delta y plus then I vx q not q2. Rather, we will write this ux, we will write p not q2 but p naught plus Then we have into delta x plus v no v it is vy yes vy p naught again p naught delta y. As you might have seen, sorry, yes, I can write it like this, but then I have to do one more thing. I have to add this error. I don't have space here. It is better to switch over to another page. Yes, write it there. Otherwise, this may create confusion for you. That is f dash z is equal to, let us begin from this. F dash z is equal to, f dash z is equal to all the points q1, q1, q2, q2 will be replaced by po. And then what will we do with the error? You will see it yourself. First, let me write it. U, it is equal to limit delta z tends to 0, delta z tends to 0. Then I have u p naught plus v p naught. No, it is again u p naught delta x, ux p naught, uy p naught delta y, ux p naught, uy p naught, it is delta x plus delta into delta y, that is this much. And then I same thing, vx p naught plus delta x plus vy p naught delta y divided by delta z delta z delta z plus delta z. Again, I failed to show you the additional term. I had to add that errors that I committed. I wanted to add them here. I will write it here, plus I will write for all of those errors as delta. Let me call that delta. What is this delta? Let us be clear about this. Plus delta, that means this expression, when it ends somewhere, divide by delta z, then there you need plus delta. You need to write this. What is this plus delta? Let me show you what is plus delta. Now, this is important. This is the point. The whole, I should say, this is the heart of this topic, heart of this this lecture, this delta. What is this delta? Yes, let us see. In first case, how much error did we commit in first case? As you remember, if I better it is to show it once again here. P naught, this is P, this is Q1 here. Similarly Q2 then. Now I had to write UX Q1. What I wrote UX P naught. This means that the error that I committed was UX Q1 minus UX P naught. This much error. Because once again, I had this term UX Q1. I had this term. And what I wrote in its place, I wrote UX P naught. That means how much error did I make that can be easily seen. That is, for example, suppose this is 16. This I wrote, instead of 16, I wrote 12. The error that I committed is difference of these two. 16 minus 12. If I add that error to this side, the two sides will become equal. That means if I write UXQ1 minus UXP naught, then the two sides are now equal. So this will cancel with this. UXQ1 will equal to UXQ1. This is the error that I committed was this. How much it was? This error was UXQ1 minus UXP naught. Oh, okay. UXQ1 minus UXP naught. Now we substituted this ux p naught here. We had to substitute ux q1 there, ux q1. In place of ux q1, we substituted ux p naught plus ux q1 minus ux p naught. This is correct. There is no error now. In place of ux q1, we are substituting this. There is no error because this and this will cancel. This and this will ux q1 will be equal to ux q1. When we substitute in place of ux q1, we substitute this here. You will naturally question me, sir, you have substituted only this part. You have not substituted this. I will now add this at the end. This is what actually will form the error, the delta. This part, which I had to write here. But along with this part, I will have to collect. See what? When I substitute this, in place of ux q1, when I substitute this, I have this situation. Ux p naught, this ux p naught plus ux q1 minus ux p naught in place of this ux q1, but ux q1 is multiplied by delta x there. You can see ux q1 is multiplied by delta x. So whatever you write in its place will be multiplied by delta x. So this whole will be multiplied by delta x. Now this part ux p naught plus ux q1, sorry, this part ux p naught into delta x is there. Ux p naught into delta x is there. But this part, the rest part, what is that rest part? Ux q1 minus vx p naught into delta x is not there. That is not there. This part has to be written at the end of this. Now that is only from this part is only from this term. Similarly, you will have a part from this term, a part from this term, part from this term. We collect this part separately and call this delta. We call this delta, and don't write. We will not write all these parts there because it will become too lengthy. So delta, and this delta will be equal to first collect this part. It will be equal to ux q1, the error made, ux q1 minus vx p naught into delta x. Of course, it will also be divided by delta z. This delta z. Yes, this is important because when you take this separate, you will have to take this delta z along with it. Plus, in fact, this delta z will be for all associated with every part. Then you have another part. Let us go to this. You have here simply in place of ux q1, you will write here uy q1 minus vy q1 into delta y. Into delta y, into delta y divided by again divided by delta, that is there, plus then we have I this I vx p naught, in place of that we will have vx q2. As you know, vx q2 delta x plus vy q2 delta y which is not visible there, delta y divided by in delta y this sorry, I'm sorry, it is not here it is, I'm writing this piece. It is vx q2 then vy q2 delta x, that is common to them, and that is to be written here, delta x. And lastly we have that last term, that is that will be this. You can understand that yourself now. It is simply this vy q2 minus vy q1 into delta y. Now the whole divided by delta z. Now the interesting thing, and after that I will not need to write delta at all. That interesting thing is this. This is the heart of the problem. The most important thing in this problem is this now. Now, what is that? As delta z tends to 0, Now, what about this term? This bracketed term, say ux q1 minus vx ux q1 minus it is vx yes ux q1 minus vx p1 vx, it should be ux p1, not ux uy. Ux p1 is ux q1 minus ux p naught, sorry, ux p naught, yes, ux q1 minus ux p naught. This is the term. Into, it has into delta x by delta z. Delta x by delta z. Now, my dear students, just check it and see. When as delta z tends to 0, will ux q1 tend to ux p naught? Yeah, that is to be seen. Yeah, let us go back to our this. Now let us draw it here. Let's do it here. This is z naught p naught. This p naught. This is say q1 here. As delta z tends to 0, my question is, will ux, value of the partial derivative at q1, tend to value of partial derivative of this so that this term becomes 0? Only under one condition. If this ux is continuous from q1 to po, if it is continuous, then you can guarantee that this term will vanish. If it is not continuous, say suppose you reach a point where this function is not defined at all, then this difference is not defined there at all. It will not, of course, it will not then approach 0. It will approach 0 only if this function is continuous from this point to this point. So that, suppose for example, this is here 2. Suppose value of the function here is 2 and value of the function here is 5. This 5 will approach 2 provided the function is defined everywhere. If it is continuous here, if a function is continuous between two values, then it passes through all the values between them. If it is not continuous, then no one can guarantee you this thing. This means that this quantity will approach 0. This quantity will definitely approach 0 if the condition is that if ux is continuous from this to this. But what is ux? Ux is partial derivative, not u. I'm not talking of u. I'm talking of ux. Ux itself has to be continuous to make this 0. That means this derivative, this term will vanish provided ux is continuous. Ux is continuous. Similarly, you can say this term will vanish provided this is continuous. Uy is continuous. Uy is continuous. This term will vanish provided Vx is continuous. This term will vanish provided Vy is continuous. That means if these partial derivatives are continuous, then this whole delta will vanish and we will be left with a perfect derivative. You see, you will be left with a derivative like this. You have the derivative, final derivative is then f dash z is equal to limit delta z tends to 0 uxpo delta x uxpo delta x uypo delta y vxpo delta x vxpo delta y yes, delta y, of course it will be there, delta y, although I have not written it, but it will be there. It is uxpo delta x plus uypo delta y. This is one term. There are other terms as well. Those are I vxpo delta x I this then I have I vxpo, I should write it here, vxpo delta x plus then we have vxpo delta y divided by delta z. See, I have not added that delta term because because the partial derivatives are continuous, hence that term will vanish. Now, of course, unless there is one more subtle thing, that is, as long as you hold on to this delta z tends to 0 without substituting it. If you do not substitute it, you just hold it. As long as you do that, you have to add this here plus delta. But since we know this thing, we can we know that delta will vanish ultimately. So let me give it up. And now here I am going to do one more, a simple thing here. I am going to instead of vx, I will use for vx I will use a CR equation. Now the CR equation, here's the rule for CR equation. Now CR equation, just a minute. The rule for CR equations, where is it? Yes, I can write it again. So I have this, I don't know. So I have f dash, just a minute for this. F dash z o is equal to limit delta z tends to 0 and delta z tends to 0, and I have then this long list of I have ux po delta x plus uy po delta y. I will try my best to keep it within this page. Now uy, then I have vx, let me go back. I have vxpo, then vypo. I have vxpo, po. I have vx I have now plus I vx okay vx po delta x plus vy po delta y divided by delta z. Now last thing, that is, I am going to use CR equations. I will convert this into this or something like this. that means not necessarily ux, I mean uy. I have a Cauchy-Riemann equation as vx is equal to, that is equal to minus vy. Is it minus vy or vy? Sorry, u. Vx is equal to. I will. No, I will combine this with this. You will see why. You will see yourself why. Vy is equal to vy is equal. This is vy. Vy is equal to ux. This Cauchy-Riemann equation. Vy is equal to ux. And if I substitute it there, I have then vy is equal to ux, and similarly I will use here vx is equal to minus uy. Using these two, I have finally f dash z o is equal to limit delta z, limit delta z tends to 0, that gives us uxpo. Now uxpo, that is okay, uxpo plus into delta x plus, I will combine this with the last with the first, vy, that is ux. Again I have uxpo, okay, po delta y, but with I. This I is there. This is vx, please. Vx. Now, sorry. This is not vx. It is vy. That vy has been changed into ux. U. Please remember, this is u. This may create a confusion, so it is better to rewrite it. uy delta y. Then I have next. This is good. Okay. Plus then I have now uypo delta y. That I will write it uy. Okay. uypo. This was po, yes. Po here. Uypo delta y. Plus this will be combined with this. Now this is vx is equal to minus uy along with I, so it will be minus uy along with I, of course, I po into delta x whole divided by delta z. Now it is easy. F dash zo is equal to limit delta z tends to 0. Then we have this. I will take uxpo common, here, and I will get inside. I will get delta x plus I delta y. That is why I combined this with this. I delta y. Because ux, it should be ux and ux. You have to take ux. I think we have again done something wrong. Vy is equal to ux. These, we have to be very careful about this. Very careful. This is ux. Vy. This was actually vy. The last was combined with the first. Vy is equal to ux. Cauchy-Riemann equation. Now then I have plus vy. Okay. If I take this vy common, again I have, this is uy. Now this is you know this is it was this uy, and with this we combined this uy, taking that common po, taking it common, I have now here inside uh, mm, I have this delta y minus I delta x, delta y minus I delta x. This I have to change because I want this, I want it like this. I want it. It is better to say this was delta x plus I delta y. Okay, then I will write here minus. I will multiply it by minus I, minus I will multiply it. When I multiply these two terms by minus I, first multiply this with minus I into minus I, that is 1 plus 1, that this then becomes uy, this becomes the first term, then uy, taking that this will become minus I uy, my take this uy common, you will have then delta y here, delta, yes, delta x here, sorry, this has now become the first term, so this is delta x minus I delta y, I delta y. You can check it, if you like, you can check it at your place. This is quite simple, delta x minus I delta y. So delta x minus I delta y, so it was minus I into minus I, that is I square minus minus is plus, it will be sorry, I'm sorry, it will be minus, it will be minus I, it will be something like this plus here. See how this is minus minus, that is plus I into I square, that is minus 1, so ultimately this will become minus delta x minus, and that minus you are taking common here, you're taking minus common, so this will be upo, it automatically is minus I upo uypo into this. I think you need to verify, simply check it like this. Let us check it like this. Here we had I here, that was there, I ivx, ivx, vx was changed into uy, yes, it was changed into uy with along with minus uy along with I, it was written here minus I uy po delta x, po delta x. Okay, then I had this term vy, vy was ux, vy was ux, vy became, this is vy became ux, so but it was combined with this. I have now these two, uypo delta y, uypo delta y, and then this term became minus I uypo delta x. Okay, I have I vxpo, I vxpo or delta x plus vy po delta y. That's absolutely correct, no problem there. But where does the problem arise? Then it becomes you have to take it here minus, common minus, then this term will come at the front, this will be delta x plus I delta y, because see why it should be minus, see why, because minus I into I, that becomes minus I, this will become plus I, that again this will be the plus, multiply this with this and multiply this with this, it is quite okay now, absolutely correct. Now divide by delta z, divide by delta z, I have forgotten to write delta z here, delta z here. Okay, and then this is delta z, this is delta z, and limit delta z tends to 0, you have ux po you can PO, UX PO, delta Z by delta Z, that is 1 minus, because delta Z tends to 0 but not 0. Let's now evaluate this limit delta, and then again UX P naught, UX P naught, I'm sorry, plus, what was it here? It was I delta X, yeah, which I cancelled, plus, then it was minus, it was not plus, ultimately it was I delta Y minus I, and then this whole thing. Now it is now UXPO, because this delta X plus I delta Y has gone, minus I, of course, and this is again delta X plus I delta Y divided by delta Z, that is delta Z by delta Z, because this delta Z by, you have UY PO I, but with I. Now PO, you can substitute for PO, you can write that is ZO, it is one and the same thing. And finally we have then this is our expression for f dash Z is equal to UX, let us go back, UX ZO, of course, UX and then UY minus UY, UX minus UY, UX minus IUY. This is the expression for this derivative of a complex function. But most important thing is that we arrived at this derivative only if we consider UX and UY as continuous. If they are not continuous, then you cannot arrive at this. You have then this, you can write, this is evaluated at PO, this evaluated PO, that can be written as UX X naught Y naught, minus I UY X naught Y naught. You can you know that UX is equal to you can change it, UX into VY and UY into UY into minus VY VX, yes, UY into minus. When we substitute it there, we have f dash Z. I'm sorry, I don't know what happens to this time and again. F dash Z is equal to, first result was UX X naught Y naught evaluated at this minus I. It was I UY X naught Y naught. And when we used this CR equations, we can, by using CR equation, we can have another expression for this, that will be UX. In place of UX, one can have UX instead of UX, one can have UY VY X naught Y naught minus I. In place of UY, one can have minus VY VX I X naught Y naught. This is the expression for this derivative of a complex function. What was the most important thing that we discovered was that this sufficient condition for a complex function to be differentiable at a point and in a neighborhood of that point. Of course, that is the sufficient condition is that it should obey CR equations, and its partial derivatives, first order partial derivatives, must be continuous in that in some neighborhood of that point. That ends our proof for this these sufficient conditions for this. The most important thing was about continuity of partial derivatives. We will now pick up some problems based on these CR equations and that we will do in next video. Thank you so much.